Yeah, maybe I should share that with the whole class, because so I just had this question about the F essentially. F is not my simulation. F is not this black thing. F is my ODEs. That's the model itself, right? It's basically your equations, whichever they are. Okay? So you have to imagine that you have this black simulation here, but this is what you need to build. It's not like you have it. Here I'm showing it for the sake of illustration, but you have to imagine that you're given this xk, the initial condition, and the uk, and then you need to build the black thing. And we'll build the black thing by replace it via a polynomial, this blue thing here. And build this polynomial such that it approximates the black thing very well. And we do that by pinning the beginning of the polynomial on the initial conditions, and by forcing the polynomial to satisfy the ODE, not the simulation, really the model, on these different checkpoints. I hope that deconfuses a little bit. Okay? We can keep discussing that if it's still a mystery for some of you. Okay, so we have these constraints essentially, and if you solve these things, and again it's really a set of equations. F are your model equations, whichever they are, whether it's a flying machine or a car or a house, and x and u are given by the NLP solver. It's your current value of xu throughout your SQPI iterations, and now you want to build a simulation for this interval. So you will, instead of building this black thing by, for example, taking Euler steps all the way, you will build this polynomial and call that your simulation. And you do it by solving these equations for theta. So you can really think of these guys as a set of equations in theta. Call them C if you want, parameterized by x and u. So you can stack them like this in a vector form. So I have all these guys. That would be, yeah. So you have the first equation in theta k1 all the way to theta kk. And this guy's, I should have an index moving. I'll check that. But you have essentially these equations together. Ah, yeah, okay, yeah. These sums change from one equation to the next via the time at which you prompt them. So tk1 all the way to tkk. So essentially these guys here, they are numbers at the end of the day. They are evaluating polynomials at different time points. And they will combine the thetas differently at each line. And so we had this picture yesterday, but you don't see much happening. So if you start the equations with these thetas and do a Newton iteration on the first Newton step already, this polynomial will basically approximate the black thing, so the true simulation in some sense, very accurately. There's a tiny difference up here, but it's not very large. And second step is pretty much on it, and so on and so forth.
Are we looking at the striped blue line now, or? Yeah,
exactly, the dashed one, yeah. Okay. So essentially that's really, so this black thing is this, I'm really running some ODE behind that. And I would start my thetas very naively if I was giving this initial guess for the thetas, but why not? And yeah, Newton would nail the correct.
Okay, so it's hard to see, I guess.
Yeah. Yeah. Well, essentially, the first Newton step, the equations are not solved very well yet, but it's already kind of on the black thing, and the second one, it's really on it. The slides are on Google Drive, so you can look in details yourself. But all I want to say is that when you solve these equations via Newton, unlike the NLP itself, this typically converges in 1 or 2 Newton iteration. It's extremely fast, especially if you start with a good initial guess. Yeah, and then what you care about is the end of the simulation, this small f xk uk, because you need to pass it to your NLP solver to close the gaps. So you care about s, or the interpolation at tk plus 1, which you get once you have the thetas. You get it by just building this sum at tk plus 1. So again, that's a set of numbers for I goes from 0 to k. That's basically a linear combination of your thetas. Yeah, I said that yesterday, but maybe I can say it again. So the only nonlinear thing in the equation is coming from f, and that's your model equations. If your model is linear, then these equations are linear. You could just solve them as a linear system in theta. Right, so that's what you report to the NLP solver. The NLP solver is manipulating these constraints in the end. And so this f is essentially your s theta for the correct theta, solving the equations at tk plus 1. So in the NLP solver, you could replace this shooting up constraints by essentially constraints that read like this, blending the thetas and the xk's in the evaluation.
If what you report is the tk plus 1, why isn't tk plus 1 a part of the time grid?
Like if you put a time check here, and then you have the theta k, the last one, yeah. Yeah, and you can do that, and some types of selecting the time grid would have a time check here. So then you would report directly. So you would have a flat constraint like theta minus xk plus 1 equals 0.
Is that something related to the collocation points, like LGL and?
Yeah, exactly. So let me remember. If you want to have a checkpoint at tk plus 1, you would need to choose a Radau collocation scheme. These ones would have these points, and this is a Legendre collocation scheme. There are, if you go far into the details, there are motivations for choosing one or another, but yeah, it's. I think I'll mention that in the next slide. But in the end, it does not really matter. This is linear in theta, right? So it's not bothering you in the NLP solver. Any linear constraint is golden. That's something that is solved in 1 Newton step. So it does not, in terms of convergence, it would not make a difference to have this last theta or not.
But what about accuracy? Because
Same.
The dynamics aren't valid at any other points
than the checkpoints. Yes and no. So in all this quadrature theory, if the checkpoints are chosen properly, the order is applies at the endpoint. So it does not matter that you don't have a checkpoint there. As long as you choose all the checkpoints by the rules, the high accuracy will be at the end, where you care about it. Yeah, thanks for the question. All right, yeah, we can discuss that a little bit, how you select these points. It would work to choose them a bit randomly, actually, but you would sacrifice accuracy. So here is a table that you can use. I said, yeah, just before. So you have Legendre and Radau collocation schemes for different cases. And the difference between them, exactly as we just discussed, is whether you choose a checkpoints at the end. So here I'm looking at time grid 0 to 1 now. Maybe I should specify that. So you would imagine that your tk is 0 and the tk plus 1 is 1. And I'm describing the checkpoints in between. So Legendre of order 1, I'm choosing just one checkpoint in between. And Radau of order 1, I would have one checkpoint at the end and always one at the first point. And you can go up in the case. I showed you this one actually, what I've been using all along. These checkpoints here, they were chosen according to this list. and you can go higher and higher. Actually, the way you build these checkpoints, I'll show you, is systematic. So if you want a grid with k equals 39, you could in principle build the time grid. Yeah, maybe actually that's interesting. If you choose a Radau of order 1, the checkpoint is at the end. And you know what this integrator is? It's an implicit Euler scheme, actually. I don't know if you know the implicit Euler scheme. You would basically choose k plus 1 equals xk plus delta t f xk plus 1 uk. That's implicit Euler. Explicit Euler would use xk here. So that's an implicit Euler scheme is a Radau of order 1. And as you move up, you have higher orders. And just as a remark, all these guys are actually implicit Runge-Kutta schemes. So if you suspect it's connected to implicit integrators, it's the same thing. Okay, why these points? That's a little bit intricate. One explanation you can try is that if you select these points, if your trajectories are themselves polynomials, then you have an exact integration. And that explains how you get specific orders of integration in these different schemes. Beyond that, it's hard to explain. The theory is actually quite involved, so it's a bit hard to present everything. Okay, so now these points are for an interval 0 to 1. Now you have TK plus 1. How you move from that to this interval? Well, you just translate and rescale. So if delta t is 0.1, you divide all these guys by 10 and you shift them to match the TK, and there you have your points. So that's what you would do here. My TK plus 1 is 0.4, so I would multiply the points by 0.4 and add 0.4 here, and then I have my points. The other way you can do it is by just applying these points and just scaling your equation. So that's just small technical details on how you can handle this thing. So in the codes that I'll give you at some point doing direct collocation, we use this kind of trick. So you would see that somewhere in the equations we multiply the dynamics by essentially delta t, the space between these points in the grid. Yeah, in the case your model, the f function is time dependent, then you need to be a little bit careful about how you deploy these things. If it's time independent, you can write your collocation equations like this. So just using these TKs here and completely dismiss the problem of shifting, rescaling the time intervals. Yeah, and that's your question before. So Radau schemes, they have always a checkpoint at the end of the time interval. So you get your theta kk, that's really the end of the trajectory. In general, if you have ODEs, I would advise you to use Legendre. It has one order more than Radau, actually, so it's a bit more accurate. If you are using differential algebraic equations, then it's better idea to use Radau, because it's tailored for that purpose. So if you have ODEs, just go for Legendre. Okay with that? Yeah, don't say that. Okay, I don't have this information, but these numbers, they are selected as the roots of some polynomials themselves. So you have a systematic way of doing that. And in the codes, we have a small function that computes the points for you for any given k that you want to use. Okay, a few remarks about the notion of stability. I don't know if you have heard that. If you have, you know about stiff systems, yeah. If you have stiff systems and you try to process them using classic Runge-Kutta schemes like RK4, Euler, and so on, you often run into trouble because even if the system itself is stable, the numerical simulation may be unstable. So when you run these points using, for example, RK4, you may just get garbage out of that because you have fast dynamics in your equations. So if you have these kind of problems, that's a very strong reason for going for this type of implicit schemes like collocation, because these guys are astable. So regardless of how fast the dynamics may be in your system, the integrator will always give you something meaningful. It may not be accurate, but it will be not be crazy. And maybe I can make a small remark about that. I don't have an illustration in the slides, but you may have like a stiff system that, for example, essentially decays to some steady state values by also oscillating around it. That would be a typical stiff system with some very fast dynamics oscillating and a slower dynamic that maybe behaves like an exponential. So if you process this with an explicit Runge-Kutta scheme, for example, it would typically just blow up and give you nonsensical stuff. But if you use this kind of collocation schemes, and you use a fairly aggressive time step, for example, the tk plus 1 minus tk is large, so you may not be able to see these small oscillations or process them very well in the integration. So what the collocation schemes will tend to do is basically kind of ignore these oscillations and just capture the slow dynamics. And they will do that without bothering so much about these fast oscillations. So when you use these schemes on stiff systems and you don't select very small steps, tk plus 1 minus tk, that would allow you to follow all these fast dynamics, the integrator will just kind of average them out and ignore them. But you still get something very meaningful for your slow dynamics, which is probably what you care mostly about.
Question.
Yeah.
Because we kind of looked at the derivative in the last to make it fit, right?
Yeah.
And here the derivative is like all over the place.
Yeah, yeah, but it still works.
It still works.
Yeah, that's a bit magic, but yeah. Yeah, so you typically, if you play with these integrators, and try them on stiff systems, you tend to see that it's kind of going through kind of filtering out this fast dynamics. Yeah, okay, you have a small difference between Radau and Legendre in terms of stability, but it's a purely technical difference. Yeah, the order of integration, we can mention that. It's actually an extremely high order. So if you have, so your k is the number of time points you choose, and the order of integration is in the order of this h, so that's the space in the main time grid to the power of tk. Yeah? So choose 2 time points in the grid, then you already have an order 4 in the integration. So that's matching a Runge-Kutta 4 explicit, for example. Radau loses one order. That's the price you pay for putting the checkpoint at the end. Yeah. Yeah, there will be a few more things to say, but that's probably enough. Yeah, this integration order applies only at the end of the integration, so at tk plus 1 if you want. So in the interval, that's kind of joins one question somewhere. Yeah, that was so you get the polynomial that approximates your trajectory throughout the tk plus 1. But the bad news is that what this S gives you at arbitrary time points inside the interval the order of accuracy you get there is a bit worse. So you cannot claim that you have the same accuracy. So this order applies to this endpoint, and that's regardless of whether you have a checkpoint on that endpoint or not. Yeah, and I said that before. Actually, these collocation-based integrators, they are implicit Runge-Kutta schemes. So you can actually write a Butcher tableau matching these schemes and see them that way. Okay, so that's technical details. We went through this. I can just show that stuff again. So it was about the sensitivities of this collocation scheme. So again, the picture here is that you build your simulations by solving your equations in theta, and then to the NLP solver you need to return the derivative of the endpoint of the integrator with respect to xk uk. That would take taking the derivative of the thetas with respect to xk uk, theta being implicitly given by these constraints, for example using Newton. And there you can apply the IFT to get the stuff. So again, we saw that differentiating an explicit Runge-Kutta scheme, that's quite expensive. You have all these A and B matrices to carry around. For a collocation scheme, it comes for free because you run Newton on your equations, you need this matrix inverse here or a factorization of it, and you can reuse it to do essentially the sensitivities doing that. So it's just very few matrix multiplications here to get the del theta del x, del theta del u, and then the del f del x, del f del u by doing that. So simulation is a bit more expensive when you use collocation than if you use an explicit scheme, but then the sensitivities are for free. So the overall cost of doing both simulation and sensitivities may actually be pretty good for these kind of schemes, depending on the applications. Okay, let's see now, so now that was building simulations by solving these constraints, right? So for each time interval tk plus 1, we have a set of constraints to solve for the thetas, and that will give us the f. And now we need to kind of insert that into the NLP solver or the multiple shooting scheme if you want. Because that's the big picture again. So you have to imagine that that's the multiple shooting scheme, the NLP from multiple shooting. And behind each of these functions, now these are genuine simulations, that's the small f. Behind each of these functions, there would be a set of constraints to solve and then this thing to evaluate. So every time you want to evaluate this function, you solve these equations for theta via Newton, and you evaluate this guy, and that returns f. If you want the nabla f, you need to use the IFT of the slide before. Yeah, so if you wanted to evaluate g, you would have to run a lot of small Newton scheme to evaluate all this f at different x and u's. Does that make sense? And in that sense, if you think about it, if we had, for example, let's dismiss the problem of inequality constraints for now. If you had an NLP solver that was to solve your KKT conditions, so these two guys, without inequality constraints, you could deploy simply a Newton scheme on solving these equations for W and lambda. And so you would take steps in W and lambda here. And each time you would take a step in W at this level, you would have to reevaluate these functions, all the f's and their sensitivities. And you would do that by solving all these equations with respect to theta. So in that sense, your problem becomes a two-level Newton scheme. You have one level of Newton that handles the xk's and u's, the red and blue things, and dual variables. And then you have Newton schemes below these Newton schemes that handle the thetas inside. could put that in a tree in some sense. You have the NLP solver that handles these equations. It's working with these variables, the W's and the lambdas. Could use Newton at this level. It could be SQP if you have inequality constraints. And then at each round of iterations, you would update the W, i.e. you would update the X's and the U's. You would pass them to your integrators, which now are basically a set of equations that are being solved. So for the first interval, you have a set of constraints with x0, u0 given by the NLP, and then you solve for theta 0, doing some Newton iterations in here. And at the end, when you converge Newton in here, you evaluate S at theta 0, t1. That gives you f of x, u0. And you do this for every shooting interval. And that's first shooting interval, second, third, kth, and so on, all the way to the end. And each of these boxes, to resolve the thetas, you do a bit of Newton all over the place, right? Does it make sense? And then you give these things back to the NLP solver. With the new x and u zeros you have computed, here is the new f for each shooting interval that will come into the G and somehow into the Lagrange function as well. It will take a new step on the W's, update all these variables, dispatch them in the integrators, update all the thetas, go back, right? You see this scheme? Yeah, so you have Newton running all over the place. One good news here is that the work you do in your integrators, you could in principle do it in parallel, right? You get this new list of variables, you pass it to all the blocks. If you had n shooting intervals and n CPUs, you could run all these things at the same time on all the CPUs. So you can parallelize this step. Can be quite.
Do you store the thetas?
Say it again.
You store the thetas between the integration steps?
Typically you do, yeah. Why? Because the thetas you do at the next step may actually be very close to the previous ones. So you can reuse them as initial guess. So typically, yes, it's a good idea to store them and reuse them. Or start the new integration using the previous ones. So okay with that picture? Okay.
Can I ask another thing?
Yeah.
How is it different from what we saw yesterday when we talked about sensitivities in collocation integration?
That's the same story. Yeah. Yeah. I'm sorry. I'm restarting from there. Yeah. Yeah. So that's exactly what we saw yesterday with a bit more explanations. Yeah. So that will be doing multiple shooting with collocation-based integrators inside. So we solve essentially what's happening here is that we solve a lot of constraints, both at the NLP level for closing the shooting gaps and at the integrator level for finding the thetas, right? I don't know if anyone see where this is going now, but you solve all these constraints separately at this level and that level. What if you were handling them all together inside the NLP solver? Because these guys are constraints in the end. It's just sets of equations to solve. What if I just plug them inside G and give everything to the NLP solver? Right? If you do that, you're doing direct collocation. That's how it connects. So you can think of it that way. So again, that's the approximation of your dynamics via these polynomials with all these constraints, essentially saying that the polynomial is solving the OD on the checkpoints. And you could build in principle an NLP that comes directly from these constraints. So the initial condition, the x0 matching x0 bar, you could replace it by the theta 0, 0. That's the very, very first theta you have in your collocation scheme. And say, I want this theta to match x0 bar. Then you have the shooting gap constraint that is now your interpolation at t1 that must match the next theta, right? So that's the end value of your the integration on your first interval that must match the beginning of the next. So that's really the f x0 u0 minus xk plus 1. That's the same thing here. And then you add to that these collocation constraints that look like this. So basically say you also need to satisfy all these guys. And you have a bunch of them. That's for the different i's in this thing. So the list of collocation constraints. So these guys are essentially the c's that you would stack inside the g function. And you have a number of them all the way to the end. And now your variables that the NLP has to handle, it's no longer the x, k's and the u's, it's actually all the thetas and the u's. And all these, the first thetas are actually the xk's, the red xk's that we had before in the multiple shooting. And the other ones are the intermediate points. So I replace my red xk's by the first thetas, and then I also have these extra variables inside the NLP. And essentially I'm asking the NLP to optimize the system, satisfy the boundary condition, satisfy the shooting gaps, and then satisfy the OD all at the same time. Okay with that? Any question? No question? That's surprising. Okay, we can make an example. So just as a warning, of course, it's an awful lot of constraints and an awful lot of variables for the NLP. But as in multiple shooting, there is an awful lot of structure in that problem. And in the computer, it turns out to not be slower than doing, for example, single shooting or multiple shooting. Okay, we can make an example. Back to the swing up of the pendulum. It's the same problem again. So minimize UK square, start down there, finish up there, stopped the ODE. And you would basically write all these constraints together. So on each time interval, you have these thetas, you need to solve for the dynamics and so on and so forth. Here I chose, we can discuss that, the setup a little bit. So I chose 20 shooting intervals, so that's the n. That's also the number of inputs you have. I chose Legendre polynomial of order 4. K equal 4, so that's order 8 in the integration. And that gives me 420 variables. That's quite a bit. For my system, I have 4 states. And if I count how many constraints I have in my G function, I have 404 constraints. So that's what the NLP solver is receiving. So that's a lot of variables and constraints. Maybe a funny trick question. So I have 420 variables and 404 constraints. So I have 16 degrees of freedom, essentially, right? That's the difference between them. But I have 20 inputs. In principle, the inputs are my degrees of freedom. So where did I lose 4 of them? Do you have any idea? I don't know if you understand my question, but yeah, okay. It's not trivial to spot.
It's the something to do with end condition?
Yes, exactly. I asked my OCP to hit the 0 point at final time. I have 4 states, that's 4 constraints, right? That's where I lost my 4 degrees of freedom. If I was to remove this guy, I would have a difference of 20, so 400 constraint, 420. And actually, I actually listed that in my constraints. So how would you implement XTF is 0? We essentially say that the end of the last polynomial must be at 0. That's how the terminal constraints would be implemented. Yeah.
So you have no cost on the state. Can you comment on that versus the terminal constraints?
Yeah, you could put costs on the states as well. I just did not here just to make it as simple as possible. Yeah, you could have an integral cost on your states.
Do you usually
So why using a terminal constraint instead of a cost? Okay, so let's put it that way. If you were to use like a cost, say like a quadratic cost on the terminal state as opposed to a terminal constraint, so first you would not hit that point because if you have any other cost than this one, then you make a compromise between the different costs. So you would be a little bit off. So if your goal is to really hit that point, it's good to put that as a constraint and not as a cost. Okay. The exception to that is if you use so-called exact penalty functions, like for example L1 penalties. You could implement or make them heavy enough that they would actually hit the mark. I would advise against doing that if possible, because these exact penalty functions are a bit hard to treat in the NLP solver. Numerically, they are not so nice. There's a lot of counterintuitive stuff in optimal control, and especially in the numerics. This may sound like very harsh to put a terminal constraint. It's actually easier to treat for the solver than to play with complicated cost functions and heavy penalties and so on. So that's better to do that if possible.
Then you get non-strictly convex cost function. Does that matter at all?
Well, the cost function is strictly convex here, right? That's sum of squares.
Yeah, but there's no terms related to the states.
Okay, you have flat directions, you mean? Yeah. Yeah, okay, that's a very good question. Yeah, so inside the NLP solver, so you have only the UKs, the cost on the UKs, and no penalty on the other variables. That's what you have in mind, right? Yeah, that's an excellent question. That's going to be not easy to answer. So the Hessian of the cost with respect to the variables is indeed full of flat directions associated to all the states and everything. The reduced Hessian will be positive definite. So once you eliminate all the directions that are blocked anyway by the constraints and look at what remains, all this will actually be positive definite. So if you remember the KKT lectures, you will have SOSC on this problem. And numerically, if you have that, it's not an issue at all. Yeah. So this non-weighted directions will not bother you much in the numerics. Yeah. But yeah, I hope that answer your question in a not completely mysterious way.
Often you want to try to reach your goal state quickly.
Yeah. Minimum time.
Yeah, but
yeah.
If you find that you should reach the goal state at TF, there's no incentive for
going fast. Yeah, you're right. So as we discussed, I guess yesterday, if you want to hit the mark in minimum time, then you would formulate your problem this way. So all your variables, t, minimum time, and you would write your OD as t times f xu and x tf equals 0. And the integration, you would typically do it on a kind of mathematical time from 0 to 1. If that's mysterious to you, there's no surprise, it's not completely obvious, but an intuition you can have with this, so t is essentially a scaling of the dynamics. If t is large, f is large, the system is moving faster. So you can unpack this a bit differently by doing changes of variables on the time and see how it changes the derivative, the dx dt. But the outcome is essentially this, that you have some kind of scheduling parameter here that will have mathematically the effect of shrinking or expanding the horizon of your problem. And you can have your t as a part of your decision variables with the u's and the x, and ask that at this final time, which actually mathematically would be at time 1, because that's where you stop the integration. And if you do that, obviously, you need to bound your input Otherwise, the solution is a Dirac pulse or a series of Dirac pulse in U, and that's not very well defined, at least physically. If you want to discuss more of that, we can, if that's...
This is generally possible in all nonlinear functions.
Yeah, you can always do that. The bad news is that it's not a nice problem to solve, so you would typically have to do it quite carefully.
And you can simply add U to the cost function as well.
Yeah, you could make a compromise between minimum time and how much energy you pump into the system via the input, yeah. Yeah. Yeah.
Can you just add the state as well as having it as end constraint? If you add the states
in the cost function? Yeah, you could have some cost function on the state, yeah. But if your goal is please hit the target as soon as you can, that's what you should write. Because as soon as you throw something else in the cost function, you will have a compromise between minimum time and something else. And that's fine if that's what you want to do, but please write optimization problems that describe what you want to do, not what some strange intuition make you believe that it's better to do. It's just a general rule that if you have a constraint to meet, write that as a constraint. Don't put that somehow in the cost for some reasons. If you have something to minimize, put that in the cost and put it only if you want to minimize that. And then check if the problem is well defined. There's actually, in practice, when you do optimization, optimal control, what happens most of the time is, so you write the model, you write the constraints on the cost function, you put that in the computer, it solves your problem, and the solution you get has nothing to do with what you expected. And what happens often is that maybe the model you've wrote is decently good but has some gaps, and the mathematics will find the gap and tell you, oh, if your objective is to do that, you should do that. And you go like, but I cannot do that with my real system. Well, the problem is that the model you formulated is not covering enough your real system to tell the computer that you cannot do that. I don't know if that makes sense, what I'm saying. But so, in short, the NLP solvers will tend to find the weaknesses in your modeling and exploit them for optimality. So when you see a solution that does not sound physically possible to implement, that means your modeling was not good enough to show the computer that I cannot do that, or your constraints were not good enough. So you should rework on your modeling. And that's something we see very often, like people, instead of working on the model or the formulation of the problem, they would try to strangely fix the problem by adding penalties and adding constraints all over the place to kind of duct tape over the deficiencies in the model. It's better in principle to formulate the model that explains to the computer what the physics can do on this system, and then the computer will understand how to compute the right solutions. I hope that makes some sense what I'm saying.
I have another question to
Yeah.
how fast you can regulate your system. If you put your error state into the cost function, wouldn't it then
Like x minus 0?
Yeah.
Yeah. Yeah. So this kind of problem, you could, of course, say something like this, for example, right? Or, yeah, 2 norm square. Right, yeah. You could formulate the problem like this. Again, if you do that, if you replace the terminal constraint by this, you will not hit the target. You'll be a little bit off, because this is not telling your computer that you want to be at 0 at final time. It's just saying, well, try to get there, more or less.
Isn't it trying to get there as quick as it gets?
No, this is not trying to go as quick as possible. If you want to go as quick as possible, tell your computer to minimize the time. Right?
Is it related to asymptotic versus finite time conversions?
Yeah, I guess you could say that, but you could show mathematically that this will not be equal to minimizing the time.
Okay.
That's, yeah.
Could you, if you have time, show
Yeah?
a super simple example of how you did do like the time scaling?
Oh, yeah. Okay.
Imagining how it works.
Yeah. Okay, we can do that. I guess a few people have this kind of problems. Let's see. I don't know. Can you imagine a problem like this, right? Like linear scalar dynamics. I want to hit 0 at final time, and I don't know, may have some given initial state. So I would write my OCP as this essentially, xut minimum t. The OD would be x dots equal t x plus u. And I would define my OCP time. Maybe I should use a different letter, 0 to 1. So when I discretize my ODE, I will essentially say I'm going to integrate over 0, 1 with this scalar t parameter. I will specify that at time 1 I need to hit my constraint. My time 1 is my TF. And yeah, maybe I have some bounds on the inputs. That would look like this. If you have any idea of what the TF is gonna be, you can give an initial guess of t equal TF. So t is really the variable that the solver is manipulating, and TF will be the physical time. And at the end of the optimization, your t, 1 over TF. So this t is just a variable. I call it differently if you want.
Might be easier if you drop the notation x dot. If you say define tau as equal to the final time t times time t, and then you do the chain rule on x. So you have
On the x, yeah.
You have
Yeah, that's true. So maybe I can show the mathematical details. So what is happening essentially, let's do it that way. Got something like this in mind? Right, yeah, we do a time reformulation. Tau would be in the interval 0, 1, right? And t is the physical time. And if you could call it the mathematical time if you want, but that's really, when you consider your OCP, you will integrate from 0 to 1, just as a scaling effect. Now, if you think of x dot, that's the x over dt, that's the physical time. And if I want to go this way, I would have dx over the tau. I guess if I do that, I should get something meaningful. And the tau dt, that's going to be alpha minus 1, right?
1 over alpha.
The other way around?
One.
T, yeah, no, that should work, no?
This is 1 divided by alpha.
What's that?
1 over alpha.
Yeah, it should be 1 over alpha, no? And that's my f model x of u. And so I can essentially rewrite dx d tau. That's the OD I'll carry in my computer as this, right? That's the origin of this scaling factor on the f. And then if I want to get so the alpha will be a decision variable in the computer, so it will basically define how the computer time, the tau, maps into a physical time. And so my physical TF, the final time I have in my real system, would be essentially the final tau is 1, so that's alpha. And that's, yeah, okay, that should work that way. Yeah. You agree with that?
Yeah.
Yeah? Okay.
And then you minimize alpha, right?
And then you minimize alpha, yeah. Yeah, but try that, solve the problem, you'll quickly see what happens. But that's the principle, you just scale the dynamics. And yeah, I was expecting alpha to have to be as large as possible, but I can check that carefully offline if you want to make sure I give you the right answer. But you can play with these things if you have open time problems. That's really the trick to do it. And then you have to think that everything is scaled accordingly. So the U's you get and the TK plus 1, they're also scaled by this factor. So if what you may end up with is that everything is scaled a bit too much and these intervals are too large for your physical system. Like, you may not want to have very long piecewise constant inputs, for example. So you may have to solve the problem a few times by adjusting your time grid until you're happy with everything and the solution you get. And you can do that also in collocation. It has no impact on the choice of discretization method. It's really at the OCP formulation level that you do that. Okay, what time is it? Oh, it's actually a bit past. Okay, let's finish that in the afternoon then, 2:15.
Sorry.